you're on the DP Labs channel. My name is Ivan and I work on developing electrostatic acoustics. A little over a year ago, I met Dmitry. He became very interested in the project I was working on. I had been working on it for quite a long time before that as well, and we started collaborating. An electrostatic sound emitter is a type of sound emitter that most people have probably never encountered in their lives. And very few people actually know about it. But it has a number of significant and important advantages, which I will tell you about right now. An electrostatic sound emitter is a type of capacitor-type sound emitter, which is quite similar to condenser microphones, but it works in the opposite way. It consists of several different and distinct elements. The first element in this assembly is these stators, which are carefully placed together, side by side, like this, in order to form what is known as a capacitor. And in between them, a very thin sheet of mylar film, which acts as the membrane is stretched tightly across the gap. The membrane is coated with a conductive layer. It is very light, as you can see. It is coated with a conductive layer, and a high voltage is applied to it to give it a certain potential. The audio signal is applied to the capacitor plates, which causes the membrane itself to be attracted to or repelled from these grids, in sync with the incoming signal. What is the advantage of this type of emitter? The first point is that the mass of the moving system is very low. If we take a standard conventional speaker, it actually has both a stationary static part and a moving part. The moving part, which consists of the diaphragm, suspension, centering washer, and the coil itself, has a rather substantial and noticeable mass. This leads to certain types of distortion, and on top of that, it also contributes its own unique and additional effects. The nonlinearity of the magnetic field, the coil leaving the working area of the magnetic field. Accordingly, there are actually a lot of different factors here that can affect the sound and can lead to some undesirable consequences. An electrostatic sound emitter is free from all these drawbacks. And I'll explain why. First of all, as I already mentioned, the mass of the membrane itself is very low. Therefore, when we apply energy and make this thin, flexible film move, almost all of the energy that is involved in this movement is efficiently transferred directly to the acoustic medium. We do not have such a massive intermediary component that could potentially accumulate or store a significant amount of energy and then dissipate it somewhere inside the system. In other words, all of the movements that the film makes inside, specifically between the stators, are effectively transmitted to the acoustic medium without significant loss or delay. The second advantage is that the film is located in a uniform electrostatic field. That is, regardless of where it is, closer to one stator or the other, it is always subjected to a force that is directly proportional to the applied voltage, the potential on the capacitor plates. This leads to the notable advantage that this particular type of sound emitter has a very low coefficient of nonlinear distortion. Another important point, which I previously forgot to mention, and which is also an advantage of such systems, is that the membrane operates in piston mode over a much wider frequency range. Let me explain what piston mode is. If we take, for example, a standard sound emitter, the specific point where the force is actually applied is this coil, which is carefully glued to the diaphragm. So initially we have a magnet present in the system. There is a coil in the magnetic gap, and when current is applied to this coil, it starts to move the entire rest of the structure. In other words, the force is transmitted from the central part to the diaphragm. But since we know that any material, regardless of how rigid or stiff it may appear, always has a finite measurable speed of sound propagation within this solid medium, it follows that up to a certain frequency, the diaphragm itself emits all the sound waves in phase with each other. That is, it manages to move in sync with the coil. When exiting the so-called piston mode, the diaphragm of the speaker begins to bend, to flex. At this point, some delayed signals gradually start to appear on its surface. That is, the central part emits sound just slightly earlier than the outer edges of the diaphragm itself. This leads to some interference between these signals. And as a result, the speaker's directivity pattern above the piston mode changes. It becomes unpredictable because certain maxima and minima appear, meaning these waves interfere with each other. They reflect from the edge of the diaphragm back to the center. Basically, we cannot predict the behavior of this diaphragm at frequencies above the piston mode. Just so you understand, the piston mode for typical sound emitters is up to about 1 kilohertz. What happens in an electrostatic sound emitter? Because the membrane is in a uniform electric field, a force proportional to the applied voltage constantly acts on every point of this membrane. As a result, the entire surface of the membrane starts to move synchronously, being attracted and repelled. So there is no delay here. This is how the signal propagates in the medium, or more precisely, as an acoustic wave. This leads to the fact that in reality, an electrostatic sound emitter operates in a piston-like mode. Across almost the entire range of frequencies, this effect can be observed. There are, however, some drawbacks related to the appearance of certain vibrational modes, primarily because the stretched membrane is still attached at the edges. For example, the flexibility of the membrane in the center is slightly higher than at the edge, which leads to some subtle differences in behavior. And accordingly, at some of the higher frequencies, these effects become more noticeable. The signal starts to reflect from the very edge of this thin membrane, and what is known as zonal radiation also occurs at this point. However, this effect is quite well compensated by the fact that the majority, if not the entirety, of the membrane's surface is still being influenced by the continuous driving force from the electrostatic field, which is what sets it into motion. Therefore, the sound emitter actually radiates everything in a very directional and precise manner. This particular sound emitter is characterized by having a flat wavefront. What does this mean? It means that the sound wave created by this emitter has what is known as a flat profile. That is, at lower frequencies, it emits more rounded, curved waves. But the higher we raise the frequency, when the wavelength of the emitted waves becomes shorter than the size of the emitter itself, they are radiated very efficiently in just one direction. However, this phenomenon, in a way, is sometimes considered an advantage and sometimes a disadvantage, depending on the specific context. But overall, it helps us, or is beneficial to us, to some extent, in certain situations. What I mean is that at high frequencies, this sound emitter actually emits sound almost like an acoustic laser. That is, if we take a sound wave and feed it into the emitter. Well, at around 10 kilohertz or perhaps 15 kilohertz or even 20 to 30 kilohertz, then accordingly, this particular area, the area covered by this speaker will gradually narrow as the frequency increases. And in fact, at high frequencies, if we move away from the playback axis, there will be no sound at all. This, on the one hand, is a potential disadvantage, in the sense that with such a sharp directivity pattern, the listening zone, or the specific area where you can actually hear the sound clearly, is quite narrow. But on the other hand, if you use this wisely, it actually becomes a huge advantage. I'll explain why. If we take a standard sound emitter of this type, or tweeters for example, they don't create a flat sound wave, but a spherical one. A spherical sound wave, as it moves away from the diffuser and radiates into the surrounding space, acquires a rather wide directivity pattern. That's how they work. And accordingly, the sound, if we're in a less than ideal room, let's say like mine here, with a lot of echo and reverberation, and like most living spaces actually, this creates a big problem for recording or listening. For those who truly appreciate and value high-quality, detailed sound reproduction, it's specifically the reflections that occur inside the room that really matter the most. If our sound emitter, such as a speaker or audio device, has a wide directivity pattern, then the sound wave, especially noticeable and pronounced at higher frequencies, which means transients or sharp sudden sounds, ricochets off the walls, and as a result, we hear a very strong and significant influence from these reflections. The room has a big impact on the sound being reproduced. A spherical wave reflects very well off all surfaces. As a result, in the listening area, we end up with a raging ocean of reflections. People perceive this as a kind of blurriness. In other words, the sound stops being focused. That is, it's the opposite of what we're aiming for. We have a left channel and a right channel. We want to achieve a three-dimensional soundstage. To be fully immersed in the atmosphere envisioned by the sound engineer. But because of the reflections, all this holographic effect, all the beauty of the sound that the sound engineer intended, dissolves in our room because everything gets mixed together. And as a result, it's almost impossible to achieve a good result without investing a lot of money in equipment. The acoustics, specifically the unique properties of the listening room, play an important role in the overall sound experience. If we use electrostatic sound emitters, then by adding an additional acoustic lens here, we can actually control the directivity pattern of the emitter itself at high frequencies, and to some extent at mid frequencies as well, which significantly improves the comfort and listening experience even in an untreated room. This is because we hear the sounds that are emitted from a directional or relatively directional sound emitter. At the very least, by positioning the speakers, we can ensure that reflections from the rear wall don't bounce straight back into our ears, but instead gradually dissipate somewhere in the room. I would like to note that the shape of the sound emitters can vary, so we are trying out different shapes. This primarily affects the range of frequencies that can be reproduced. But of course, I also see the potential need for some additional customization in the future. That is, if we have any special or particularly interesting design requests for a unique or unusual shape, then as long as it doesn't compromise the sound quality, we'll be able to cut them out. In different shapes and sizes. I've actually had a lot of different prototypes over the years. The ones you've seen, the 20 centimeter ones, from edge to edge they're 20 centimeters. After a lot of trial and error, I eventually found that this is a relatively optimal shape and size. However, that doesn't necessarily mean they can't be different actually. Here I have a small simple stand that I use specifically for tuning the sound emitters and in general for making and assembling them as well. Of course, it's pretty rough and not particularly sophisticated, but on the other hand, I managed to put this thing together very quickly, and it does its job quite well for my purposes. Sure, I spent some extra time dealing with this less than perfect technology, but it works nonetheless, and I can rely on it when I need to. So, what exactly does this thing consist of, and how does it help me in my work? There are two rings between which the membrane is clamped. And underneath, one of the stators is carefully inserted into place. The membrane itself is then tensioned by gradually screwing in the bolts, making sure everything is secure. So, as we keep tightening these bolts further and further, in the future, maybe I'll use a lead screw for this process instead, which could make it even easier and more precise. Replace it, the higher it rises. The main plate here, the higher the resonance frequency of the membrane itself becomes. In other words, as it gets tightened, its elasticity increases and the resonance frequency goes up. This is necessary to control it properly. Here I have the electrical part assembled, meaning an amplifier is used here. There's a processor there that can generate different tones for me at various frequencies, as well as a high voltage source. And so, at this stage, we proceed to carefully attach this second part. Our membrane, as a result, gets charged from the high voltage source, and then I apply a sinusoidal signal of a certain specific frequency to the input. For example, if I want to tune them higher, say to 90 Hz, I apply a 90 Hz signal to the system. And by adjusting these screws with careful precision, I achieve the membrane entering into resonance, meaning that at this particular frequency it will be in resonance. If it isn't additionally damped, the system's quality factor is quite high, which in principle is later compensated for by a special amplifier designed for this purpose. But it's precisely this simple device that allows you to tune the membrane itself to a specific frequency. Thus, even with only a very minimal amount of financial investment, I get a completely expected result. That is, I am able to produce small batches of these panels with the specified characteristics. Another reason why I specifically chose this particular shape for the sound emitter is that you can assemble an array from them, which makes them quite versatile for various applications. A larger one. So if we set up the production of these small sound emitters, which are compact devices designed to produce sound, they can be combined into a wide variety of different configurations. One of the somewhat unusual and interesting projects is this particular kind of sound emitter. The plan here is to install a total of 12 of these speakers. By combining sound emitters in this way, I want to achieve really good, deep and powerful bass. This approach should help create a much richer and fuller sound experience overall. Not everyone would probably want to have something like this. But still, we decided to try, so to speak, to grasp the ungraspable and to see with our own eyes exactly where the limits of possibility truly end. Is it impossible? No. It's necessary. Another key drawback of classic electrostatic sound emitters is that in order to match it, the sound emitter to match it with a standard amplifier, audio transformers are generally used. That is, to get sound, we need a relatively high voltage amplitude and a low current. But standard amplifiers typically produce a low voltage amplitude, well, relatively low, and a high current. That's why audio transformers are commonly used in these situations, but of course they are not perfect solutions. They have many drawbacks and limitations, including one of the main and most significant ones. In order for an electrostatic speaker to sound good and loud with high audio quality and sufficient volume, we need a signal amplitude of several kilovolts, which is quite substantial. This requirement makes the design and operation more challenging. An audio transformer with such a transfer coefficient does have some inherent imperfections, which are associated with the fact that, first and foremost, given the permissible and allowable dimensions of this transformer, it is not possible to obtain a full and complete bandwidth that ranges from 20 Hz all the way up to 20,000 Hz. And even achieving a bandwidth that extends from 100 Hz to 20,000 Hz is, in practice, quite difficult. Here is one of the transformers which is constructed in a fairly optimal manner for use with large panels. These are transformers that drove panels measuring 0.5 meter by 1.25 meter, if I'm not mistaken. Well, approximately you get the idea. So this transformer can operate in a frequency range from 150 to 20,000 Hertz. If we wanted to go even lower in frequency, that is, well, 150 Hertz is already mid-bass. And not every subwoofer can even achieve these frequencies. So we end up with a problematic range, for example, from 80 Hz to 150 Hz. The transformers are quite hefty. There is actually a second way to solve this problem, which unfortunately no one among current electrostatic manufacturers uses. This involves making use of a specialized amplifier that is specifically designed exclusively to work with a capacitive load and with a high output voltage. Basically, that's what I'm working on. Transformers are expensive, heavy, and impractical. Here is a prototype of the amplifier. The circuit is assembled on a breadboard. At the moment, this amplifier can deliver a peak-to-peak voltage. 2000 volts? That is plus 1000 minus 1000 volts for a total amplitude of 2000 volts. This is enough to achieve a volume level suitable for home use. What are the advantages? That is, it has a full frequency range, the ability to operate. In fact, it is specifically designed for this, and some circuit solutions were implemented here to ensure stable operation with a capacitive load, and with a rather large capacitive load across the entire frequency range, that is, up to 20,000 Hz. Because in reality, electrostatic drivers themselves are almost unnoticeable for the amplifier at low frequencies. But at high frequencies, their impedance drops significantly, and this causes major problems. The advantage, though, is their compact size. In the future, we really want to make it so that this device can be powered by a relatively low voltage, around 12 volts. That is to use converters, and here we will also need to add a digital signal processor to enable correction. And equalization, if necessary, should also be considered, because no matter how wonderful or impressive the acoustics are, they still require some subtle tricks. If, using the classical method, manufacturers of acoustics used to try to correct the amplitude-frequency characteristics with the help of certain specific physical dimensions, carefully selected material configurations, various types of damping elements, and different types of resonant components. All of these elements were thoughtfully engineered to achieve the desired sound quality. Like the enclosure, bass reflex, and similar types of acoustic design, now it is much simpler and cheaper. In fact, it's much easier to use digital signal processors, which allow you to adjust the signal right at the input of the speaker system. They can modify the audio signal in certain ways so that the speaker system, together with the amplifier, works in harmony and performs well. Feedback. Of course, that's also possible, but we'll think about that later. So, after all, I do have a strong desire I have a strong desire to develop an integrated system consisting of speakers and amplifiers specifically designed for them, which provide the purest, best, and highest quality sound. On top of that, I do my best to reduce the cost of these things as much as possible. Because we all know that many people love to listen to music in high quality, but they simply can't afford it financially. That's why I try to save on everything I can, but never at the expense of quality. As a result, we will get a product, or at least I really hope that we will get a product that is accessible to many people, to a much wider and more diverse range of people than is currently the case, since electrostatic acoustics are quite expensive at the moment. We really want to make this happen. It's a more democratic approach,